And then we wait for this thing to pull up.
Big slideshow.
Yeah, lots of slides.
So I can see all of them.
So close to being ready.
Rob's like.
Oh. Okay, then this thing's being funny now. Now does that work? Yes. Okay. Okay. Stop. Yes. Okay. Nope, that stopped working. Amazing.
You can't go full screen anymore.
Yeah. I was hoping I fixed it. But... Okay, so we can't go full screen, but we'll be mostly full screen. It's a short PowerPoint. So basically, just a quick reminder, reverse engineering is, in fact, due very soon. Please consult the calendar. It is September 16th. On the 21st, reverse engineering will be due. So get your Jan 85 done now. You want those points. I've pulled some legacy memes about Jan 85 just to give you some extra motivation. You can put it on your resume, and it's got hands. So basically what we're going to be demoing today is talking about structures. I asked everyone what they wanted. I got an overwhelming amount of responses for, I don't know how to reverse structures. It's hard. Please help. So we're here to help. And so recently, a new demo has hit the dojo. And it's in our demo dojo, which is somewhere right there. So I've added a new dojo or a new challenge called Strip Mine. Let me restart that really quick. Now, let me make sure I can see my Twitch chat. It's not showing up. Yeah, I try to see my. Whoa. Where did I get? Oh, yeah. All right, there we go. Okay, so in this new demo, we're going to notice that you get a binary, and this binary, when we run file on it, we can see that it is indeed strict. Let me make my text a little bigger. There we go. That. Okay, and so what I've got going on here is a challenge that is intentionally very not verbose at all. Like, you send it some input, we get collapse. Like, there's not a lot of input output to work off of here. And this is intentional. And so there's a lot of things that we can start off with doing with reversing. Oh, that's funny. There we go, I hope. Okay, it's moving again. And so I'm just going to dive straight into IDA. Obviously, there's some steps that you would want to do first when you're doing like reconnaissance on like a new challenge, like run strings, run checksec, like probe the program a little bit, see what happens. But in the interest of time, we're just going to kind of jump right into IDA. And remember that these are all things you can do in Ghidra. These are all things that you can do in Binary Ninja. You can even do them in anger management if you have some sanity to lose. Let me see if I can make this a little bigger. That's too big. All right. Yeah, it's totally fine. All right. So first things right away. Last week, I told you guys about a mythical workflow that existed for strict binaries where you want to put breakpoints at offsets. Because one thing that we found annoying about strict binaries, right, is that relative breakpoints are a little bit of a pain sometimes, as I'm sure you've all discovered by now. And so I wanted to quickly just show off one kind of definite workflow to kind of work around this. I can make that a little bit smaller now. And this is something that is going to be important. So I need my from component import star. I need my classic context.terminal. And normally when we try to do, let's see if I can just get, yeah. Let's go challenge and then strip mine. And normally when we want to set breakpoints in this program, we run into a problem where I can't just do break star main because GDB doesn't know what main is. Similarly, like if I wanted to try to make like this, like main plus 40, like maybe there's something there that I'm interested in, like this becomes difficult, right? And so what I wanted to show you was a gef macro. And basically this macro is this $_base thing. So I'm going to highlight that right there. And this macro, when you use it, will give you the base address of the binary in that current run for gef. This means that, remember, this is coming from your procpid mappings file. So this address that we're getting in $_ or $_base is the base address of the binary for the current run that we're on. So as you can see right now, it's this 55A727. And if I went ahead and spawned another one of these processes, put these side by side, and then I print out this base macro as well, we can see that it's changed because I ran the program and it re-randomized where it was loaded into memory. And now I have two different base addresses from two different runs, but that macro is letting me resolve it. This means that we can set relative breakpoints in our Python script and then begin to interact through pwn tools. So we know that we can pass a GDB script into this function here. And so I will say, let's go break. And then I want to go at this base macro. And then let's say that I want to break somewhere. So let's find somewhere interesting to break in the binary really quick. So remember that we know what main is because it's always given to libc start main. And so let's say I want to go into main. Then I've got this amazingly nasty looking function here. It's really not that bad, but let's say that I see a read call, right? And so one question that I might have for like my read call is like, okay, well, where does my data end up? Like, what does it look like once it's entered into the program? And so maybe I want to break right after this read call just to kind of get my footing, maybe take a look around, see what's happening. And so I can find my read call is at offset 101B. And then I can come over here and say, okay, I want a breakpoint at this $_base thing plus my offset 101B. Now, note that this is working because I have rebased IDA to 0. Like by default, in a PIE binary, IDA is going to be rebased to 0. Just make sure that you are rebased to 0, or else these offsets are going to start shifting around and not be lined up. And so now if I run this, let's see, the extra parenthesis. Oh, I'm missing a parenthesis. Come on, that one right there. And so now when I run the program, you can see I've inserted this relative breakpoint through this GDB script. And so now when I continue, I can break on that read call. And this is something that I can now repeat every single time, and I don't have to worry about it again. So I get a new process, I get a new breakpoint. And now I don't have to worry about going in, calculating the base address, adding it to something. Like there's like this 4 or 5 step process that we've now just automated essentially. Now, one of the things that I wanted to show off was gef has the ability to name breakpoints as well. So when you're in a stripped binary and I hit this breakpoint, I might not know immediately what it is because maybe I have like 15 breakpoints or something ridiculous like that. And so gef has this command called nb, or name-break. And what we can do is we can use this to set a breakpoint and then just give it a name, and gef will print it back to us. And so it's a really, really minor thing, but it's something that might be helpful. So if I just do nb, and then we said this was like read call in main, so I'm giving it a label. And then once again, oops, giving it that address. Go away. There we go. So nb for name break, giving it the name, giving it the address. And then when we run this, oh, what happened? Unrecognized arguments. What's going on there? Does this have to be one expression? That's why. Okay. Gotta not have spaces in there. All right, but then when I run this, I get that breakpoint. And then now when I get there, I get this little extra printout at the bottom that says, hey, I hit this breakpoint and here's what it's named. And so now I instantly know in my head, okay, this is the breakpoint that triggered, rather than you having to memorize this mapping of like what this breakpoint number means and that breakpoint number means. Very easy to do. Any questions about those two little steps there? Just something useful that you can use to automate your workflow. All right, so now let's actually dive into reversing. Let's close all this stuff. Okay. So there's this black bar here. Why is that there? Okay, we're blaming the page. All right, we're refreshing. All right, there we go. Interesting. So we're in our stripped binary. I'm going to get rid of my console just because I don't need it right now. And I'm going to kind of set up my IDA just the way that I like to do it. So I drag one of my views over, I synchronize them. And so now, like when I click on a line of source, it's going to jump to that line of disassembly. Question.
I wasn't paying attention. Did we run this thing? You know what it did?
Yeah, it doesn't print anything. No, it's reversing. But yes, if you run it, you can feed it some input and it gives you some output. But we don't really know what this means yet. It just tells you that you've collapsed. And so what I'm always trying to do when I'm reversing is just trying to like break up the program into pieces and sort of just start sluicing off bits that I don't care about or that I can focus on later. So when I initially start looking at a program, like obviously like I ran the program, I don't really know what's happening based off of just running it. And so I'm going to instantly start looking, okay, well, we have a malloc. Malloc gets checked. I have an if statement. Obviously, malloc's probably going to succeed. And then I'm going to read my program. And so it looks like we have some like just like does things before input function here that I can just name and kind of think about later. And then I have my read call. Read goes into this v3 variable here because it's that second argument to read. Let me make my font a little bigger too. Let's go 11. There we go. So we're reading into v3. And so I'm instantly just going to be renaming that. I'm hitting N on my keyboard to rename a variable. And then we can start looking, okay, well, what is happening here? How is this used? And it turns out we duplicate this pointer into v5. So pointer to input. Okay. And then I'm going to start looking for like how this is used. And based off of just some pretty basic code reading, we can see that this pointer to the input is handed to this sub C78 and then immediately freed directly afterwards, if I'm assuming this function succeeds based off this check that I'm seeing. And so this means that this function C78 is very important to me because I'm presuming based off of what I'm seeing here that this is doing some kind of input transformation, because why else would it just discard the input otherwise? And just to like confirm, I can also go, okay, well, C78 is returning a pointer. We have this if pointer where things happen. And then we have this else case that says error processing input. So now I really know what this function's doing. Like error processing input, the function's probably processing input. And so I can rename this right now to just make an assumption. And then let's see, what else can we find out just from vibing through main really quickly? We have this sub that's taking v9. And if we look at v9, it looks like v9 is in the does things before input section. So maybe we'll think about that a little bit later. And then I scroll down, I see this pointer here where it looks like we're doing some basic while loop, do while loop that's freeing things. So that's something maybe to keep in mind. But since it's not ostensibly going to help me reverse the binary right now, I'm just going to ignore it. Like it looks like cleanup code. And so I get all the way down to the bottom and I'm just seeing, okay, error conditions, like ways to exit the program. And so I kind of have a basic idea of like what's happening in this program already. Like we're setting something up in this function. Wow, I can't use the back button on my mouse here. We're setting something up in this function. Then we're taking some input. We're processing our input somehow. And then we're doing something else, presumably like with our input somehow. And so now I'm going to start to dig deeper. I've gotten this basic idea of like what the program is doing. Now I want to start digging into each of those little processes to kind of expand. Are there any questions so far? Nothing.
To like save your note in IDA so that like later when you go back it's still there.
Yeah. So what we can do is we can save what's called like an IDB. So you go to File and Save or Save As. Basically, you'll be able to save this I64 file. And that, when you load it back in, will have all of your renamed symbols, retyped stuff. Just note that it's only for that binary. So like you can't, like, for example, reverse the teaching level of like Yon 85 and then take your IDB and bring it over to like the testing level. Like it's binary specific.
Oh, God.
And so that's why we always encourage people to take external notes as well. And so like one thing that I'm very quickly going to do throughout this is pull up a notepad document and just start writing things down that I'm noticing. But with that IDB, you can just come in and open it up, and then it'll load the binary, load the file, load all your symbols. Just note that it is unique to the binary that you're working on. So now that I've kind of got this rough process of like something happens, my input gets processed, something else happens, I want to start looking into each of those buckets and just start to dip my toes in and get an idea of what might be happening. So if I go into like this does things before input function, it's already looking pretty nasty. And so there's a lot of things that I'm noticing right away. So we're only taking one argument in, and this argument is a pointer, like that's what IDA is telling us. And we can see that some pretty common pointery operations are happening to this. So we're incrementing it by 1. We can see kind of right here that we're writing to this pointer v1 and incrementing it, setting it equal to something. So that's interesting. I'm also seeing down here that A1 is being written to again. So we take the address of A1 and then we dereference it. So we're getting back there. And similarly down here, it's happening again. And so right away, this suggests to me that A1 is some data pointer. A1's being written to. There's something important being set up here that previously didn't exist in the program. And there's easy ways to do this. There's hard ways to do this. You could sit here and reason about the decompilation. You could go into GDB and look at the result of the function. There's like a bunch of different like workflow paths from here if you want to keep digging into this. And so I want to just kind of dip my toes into both of them before going down my preferred route, which is I'm an IDA guy. I like being an IDA. I like reasoning about source code rather than the bits of hell down in GDB. Note that there are some times where you have to do this. Like we'll see that later, but let's take a look in GDB and just see what we can find. So once again, I'm going to use that relative breakpoint process. So I need that from opponent port star. I need that context.terminal line. And then I want to break right after this function returns and kind of just see, okay, what is in this pointer? And so I think the easiest place for me to do that would be probably right here. Because if I come in and look at the disassembly on this last line here, we can see that we're just moving a 0 to exactly where RDI is pointing to. So that suggests that the value for A1 just remains in RDI this entire time, or presumably just gets put back there eventually. And so I want to break right here and go, okay, well, what's in RDI? And then just what data exists there. And so that offset was at C71. So just come grab my old one right here. And we are going to label this because we want to use our tools. So this is going to be after init function or some kind of init function that we've got going on here. And so that offset is C71. And let's just take a look. So I'll continue here. And then now we're right at the bottom of that function. I didn't have to do any complicated math. Just remember that base point is being calculated by Gef for you. Like you should know how to do this process in your head. And we can start digging. So I'm just going to quickly take a look at what's in RSI. It's this pointer. I really like this tele command in GDB or Gef. It's a Gef specific. And it looks like we've got some data in here. But it's not exactly obvious like what the data is or exactly what's happening here. Like, I think maybe we could maybe assume that there's some 4-byte ints based off of seeing like half of Fs, but there's not really a lot of conclusions I can make from this. Like I'm looking at this, I'm not really seeing much. So then the question becomes, oh, I was looking at the wrong pointer. No wonder I didn't see anything. I need to look at RDI. Ah, now look at that. Looks something's falling out. And so now something else has happened. We actually looked at the right pointer and saw that, okay, this function is in fact actually doing something. And we could try to dump this data out. We could try and look at it. For now, I'm just going to acknowledge that something interesting is happening here. And then I want to dump this string out. So there's a great command in GDB to do this. It's the memory dump command. So if I do memory, we can see, or sorry, it's dump memory. Dump. We can dump memory. And first, I need to find out how long this string is. So if I come in here, I'm going to grab the address of that string. I'm just going to do x/s on it. That was not as helpful as I wished it was. So we'll do it the old-fashioned way. Printing a lot of it and looking for a null byte. Looks like we run a whole bunch from here all the way to this trailing null byte right here. And so this bank of addresses is going to be A8. This is going to be B0, B1, B2, B3. So it looks like we're going all the way to B4. And then I'm just going to pull up an IPython and start doing some math. So my preferred note-taking app at this point has become IPython, just because it's an interactive note taker that does math for you. And so I can say like observed end of buffer. And I'm calling this a buffer not because I'm trying to pwn it, but just because like that's the way that I'm referring to it in my head. And then I'm also grabbing the start of that. Then we can subtract them. So that, oh, come on. Take the difference between those two. Take the hex of that. Okay, we've got a string length to start looking at. And so now I want to dump that out. So we know how long it is, 396. And so I can go memory, dump, and then, or sorry, dump memory. Dump memory, spell things right. And then we're going to give it, let's see, I don't remember the exact syntax for this, which is why we have a help command. So it's going to be the arguments are file, start, and stop. So we can go dump memory, and then we'll go some string. And I want to put this, make sure this writing somewhere that I can actually write to. And then we have our start and end addresses. So starting here, ending right there. Make sure we split those up. All right. And so now I can go and actually grab this data. So I can say with open, let's go home hacker. See, this is something I've done before. There's a DMP, some string, read bytes as f, and then d equals f.read. And now I have my string. Nice and fancy. Now, I don't know what this does yet, but I've snapshotted it. I've seen it. Now I can refer to it whenever I need to. And one thing that I also could do is like, maybe I suspect this changes run to run. So maybe I want to go and observe this twice, for example. But I'm looking at my program. I'm not seeing like random behavior yet. And so I'm not going to make that assumption yet. And so now let's kind of start to investigate like what's actually happening here. And this does things before input. Like we know this is somehow constructing a string, or at least that's what we hope is happening. Like that's the assumption that we're working off. And if we head back and just kind of peek at GDB again, let's see, can I print out RDI again? I think it's RDI, right? Yeah. So we can see some of the effects that we noticed. For example, we knew that based off of the very last line in here that we're zeroing out the first 4 bytes. And we can see that just by confirming, like, for example, like if we didn't know that this star A1 equals 0 was doing a 4-byte operation, we could go look at the decompilation or disassembly, sorry, see dword pointer. That's how we know that it's 4 bytes. We could also reason about the type of A1. So right now, A1 is pointing to a dword pointer, or it is a dword pointer. So when we write to it by default, we're going to get a 4-byte operation. And so what are some things that we notice? So I see one do while loop. I see a second do while loop. And then I see a third do while loop happen. And so to me, my brain instantly goes, okay, 3 patterns, 3 chunks. Is there something similar happening between these? And so the first thing that I want to do is just reason about like what this first loop is doing. And so we have this v1 variable that's getting set to a1 plus 1. And we know that because a1 is a dword pointer, this is going to be incrementing by 4 bytes. And so every time in this do loop, we have 2 nested of them, actually. So we have an outer do loop that is setting v2 to v1 plus 20. And then it seems like this inner loop is writing in a 20-byte chunk by just incrementing. And here's something that is misleading in the decompilation that we can kind of see, which is that A1 is passed in as a dword pointer, but then on this line right here, we'll notice that the data type of V1 is a byte pointer. And this conversion right now is a little bit transparent, like we can't see it. And so when we write down here, it might make sense in our head that goes, okay, that's a 4-byte write, but it's actually a 1-byte write because the type of the pointer changed. And so this is something that's very annoying to me, just like reading it. These are the things that as a reverse engineer, you just have to consider and like learn over time. But if we come in here and we retype this pointer from being a dword pointer to instead saying, okay, well, we think this is writing characters because we've seen that it's constructing a string, and we've seen that this write, it's only writing 46, like that's 1 byte. And so I'm making an assumption that by changing this to like a 1-byte wide data type, so a char in this case, that something will clean up. And we can see that things do actually get a little bit cleaner. We can see, okay, V1 is equal to A1 plus 4 now. And then this starts to make a little bit more sense, V1 plus 20. And then we are going to increment V1 and write a 46 there every time until these 2 values equal each other. So we advance the pointer 20 right away, and then we write, it looks like 20 46s there. And maybe we want to come in and go, okay, what is 46? 46 is a dot, it turns out. And if we remember back to that string that we exported, we saw a lot of dots. So we're already getting somewhere. And so we have an inner loop, we have an outer loop, and we have, so while A1 plus 404 is not equal to V2. Now, what does this suggest? Because there's an implication that happens right here in this loop that instantly starts to distill information that we can extract from this program. Like, what's one thing that we can assume from here? And sorry, can you repeat louder?
Right, 404 more bytes.
So yeah, so we can think of this, we can look at this size. Like we have a size for this loop, like it's going to A1 plus 404. And we've learned that it's writing 1 byte every time in these chunks of 20. And the only thing we have to keep in mind is that V1 starts from A1 plus 4. So by going to A1 plus 404, this means that in total, we're writing 400 bytes. And we could confirm this theory. Anyone have an idea of how we could literally go and confirm this right now?
Take the length of your string.
Yeah, we could take the length of our string. That presumes that I exported the right amount of bytes, though. But we're in GDB, so we can just take a look here. Let me use a better way of doing that. So we can see that it looks like our string ends at like hex 188, but let me get that other view back. And we did do the math. But one thing we might have missed is, let's see, did I get the top of that string right? One thing that we might have missed is the very first 4 bytes of the string, because when we tallied, Telly did not see those first 4 bytes for some reason. And so I think I blindly made the assumption that the string started at 528. but we know that based off of IDA, the first byte we're writing to is the fourth byte in. So right away, there's like an assumption mismatch that I've made that I need to correct. And this is kind of the game you play when you're reverse engineering, is you make some guesses, you go in, you confirm the guesses, and we kind of slowly build up a knowledge base of the program. And so we know that I'm still broken at that same point in the code, by the way, like returning from that init function where we can see RDI. And so let me actually xgx RDI. X4EGX. And so our hypothesis now is that our string is going to start right here, which is going to be at 2, 4. So I'm going to grab that and then change that to a 4. And then we can keep looking and see that it looks like our string is ending right here at V4 as well. Just we did confirm that earlier. Grab that line as well. Change that. And then now we get that 400 number out. Boom. Any questions so far? Okay, so once again, like we've gone in, we made an assumption, and then we confirmed the assumption. And so what we've got here is we've got a string that, or we've got a nested a pair of loops, essentially, that is initializing 400 periods. And I could write a note here. So if I hit the question mark or like the slash key on my keyboard, it'll pull up a comment, and I can insert a comment in IDA. So I can go initialize array to 400 dots, something like that. And then I can just write that down, and then it's there, and that it's saved in my IDB as well. One reason that I suggest taking notes externally like this is because then if like there was another challenge in this sequence, you could transfer that knowledge over rather than having to try and like juggle them back and forth. But for this case, there's just one challenge. It's a demo challenge. So I'm going to put my notes in IDA. So next thing we've got to do is conquer our next loop. And we have this weird double loop going on here. And then now in this loop, we see something a little bit different going on. We have this V3 that's being set to this unknown, which if we double click on it, it turns out this is a symbol in the data section. So this is some program data that exists in the built binary. So I could just call this like data 1 or something. Like I don't know what it is yet, but we knew that this loop was initializing everything to dots. And if we go and look at our output, or not that output, we can see that we got a string with dots, hashtags, and dollar signs. So I'm basically making the assumption that these two loops are going to be writing those pounds and those dollar signs onto this string because we know for sure it's not happening in the top loop. So if I come in here and I change this 35 to a character, I get that hashtag out. And so now the question becomes, okay, well, like where and why are these hashtags appearing? And note that this is a pretty like rabbit hole-y approach to doing this reversing. As you can see, I'm going quite in depth with this function. If I was doing a CTF challenge and trying to solve as fast as possible, I might try to be a little bit more breadth first on my search, like going, okay, what's this, and this, and trying to get a rough understanding rather than like diving into the specifics. But when you have a lot of time, you can afford yourself like the ability to go in and just look, comb through by hand, make sure you're understanding things end to end. And so we've got this funny line right here that says A1, and then we're indexing into it, 20 times the dereference of V3 plus V4 plus the dereference of V3 minus 1. And so that right away is something where it's like, that's just kind of funny. And so I'm going to pull it out. Let's find the wonderful get it. And we can begin to think about what's happening and why. So first off, remember just order of operations, like what are the things that are going to happen first? First, we're going to resolve our dereferenced pointers. And we know that this V3 is pointing into this data section, which if we look at our data section, okay, V3 is an in pointer. And we can see that presumably it's pointing to the first 4-byte int, which in this case looks to be 0. So I have 4 zeros. So that would make me just like want to go, okay, on the very first run, this V3 is going to be 0. Note that because this is in our .data section, I'm assuming that it's not going to like be changing run to run. Like I'm assuming that it's a consistent buffer. And then also we have this V3 minus 1, which is a little bit interesting, but we'll go back and take a look. So we know that V3 is going to be initialized right here. And if we look above this, we can see some IDA doing IDA things where we have DB for bytes, but we see an 8 and a 0. And then we see this weird align 4, which is basically IDA trying to tell you that, hey, this 8 is aligned. And so really what this is 8000. And so once again, that Endian representation of the number 8. And so we can take that back to our notes. We put an 8 there. Okay. And so then what's going to happen is we have this interesting pattern that's going to distill out eventually. So A1, 20 times 0 plus 4 plus 8. And then now the question becomes, okay, well, why is there a random plus 4 there? And we remember that one of the things we found very early on was that in this first loop, we can see that V1 is being set to A1 plus 4 and then written to. But instead, in this loop, A1 is just having 4 added to it every single time to account for that offset. And note that this is because I've enabled a ton of compiler optimization for this challenge to make it more difficult to reverse. And so if you, for example, were building with like O0, you might see this be a little bit nicer, but not every program is built with O0, sadly. And so we know that this 4 is just like a static offset. And so I can kind of ignore it a little bit in my head for now. I just note that every single thing is going to be offset by 4. And now I'm looking at a very pattern that you as a reverser will learn to recognize, which is a 2-dimensional array. And it's because what we have here is we're loading 2 constants. So we're loading V3 and V3 minus 1. And then we have this 20 here. And this is essentially saying, okay, I want to get to the row that corresponds to that first number and then offset into that row with the second number. And so you could think of it as almost like 20 times, I think, y plus x, for example. And it's because if we define an array in C, like, for example, height times width, and maybe we say that, like, let's just say this is 4 by 4 for now. So A1, 4, 4. And the way this is stored in memory is row dominant, meaning you will have one row, and then directly after it, the next row, and then directly after it, the next row. And so we would literally have like A1, 0, 0, then A1, 0, 1, and so forth. And then literally directly next would be A1, 0, and so forth. And so this means that in order to get there, we can just use a linear equation. So I can say that my target index is really the column that we want to go to times the width. So y times our width, plus the offset that I want to get into that row. So if I wanted to go to the coordinate 2, 2, yes, question.
Your editor is being cut off on the screen. You could bring it to the right.
Oh, that's embarrassing. There we go. That's fixed. Thank you. Okay. And so we can turn this into a linear equation to basically access that. I hope that, is that showing up now? Hopefully.
Yes.
Yes. I see a heart in the chat. All right. And so with this, we now can start to reason about, okay, well, this is a 2-dimensional array. What happens? And based on some of the numbers I'm seeing, like I see 20 here, I see 20 here, we know that we're writing 400 bytes total. What is the guess that we could make about the size of this grid? So if we have 400 total bits of data or pieces of data, and then we know that there's like 20 rows. Yeah, so that's 20 by 20. And so I can write that down. So I can say, okay, we are forming some 20 by 20 array, and just make a note to myself. And at this point, it becomes, okay, well, what is happening here? Like we load a value from V3 in here, and then we load a previous adjacent value into here. And so this suggests to me that this data1 array here is storing positions of where these pounds are going to be slotted into. And we can actually try and confirm that. Like, once again, like we have the string, which I'm going to have to re-export from GDB. So let's rerun that. We decided that this actually starts at 24 instead of 28. So let's rerun that. And then now if I take the length of D, I should see that 400. And then I can see what happens if I split this up into like a 20 by 20 array and then just print it. So the naive process in my head would just be like, let's say chunks of 20. Wow, how would I do that? Let's go X I to I plus 20, or I in range 0 to 400, and we want steps of 20. Oh, that should be a D. There we go. And now I can see that there's a grid that's popped out of this. And so we made the assumption in IDA, like, hey, we think this data array is writing # somewhere. And we know that the first two numbers are an 8 and a 0. And if we filter those in, so actually I already put that in getter, so we can just take this. So let's take this. We know that our first value is an 8, second one was a 0. And so we would expect to see a # show up at that location in our printout. And if I go 0, 1, 2, 3, 4, 5, 6, 7, 8, we do see a # appearing there. And at this point, like, I could start checking even more numbers. I could start like really trying to confirm my assumptions, but personally, I just run with it. Any questions about this so far? Okay. So now the question becomes, okay, well, we know what's happening in this function, but how can we help IDA make sense of what's happening in this function to make our lives easier? And so we've already got something going on here. We know that the first 4 bytes of A1 are reserved for something. And so right away, like, I have a structure with 2 members that I've discovered. So if I want to create a new structure, we're going to go to View, Open Subviews. We're going to go to Local Types. Then I'm going to add a type. And the only things that we've discovered so far is, let's name a struct. Let's just call it data. And we've learned that there is an int and that we have some kind of, like, I don't know, like game board that is 20 by 20. That's all we got so far. But now that I've just discovered that little piece of information, if I come in here and I retype A1, we can start to see that my decompilation cleans up significantly. Now, one thing is that IDA does kind of have some weirdness with like 2D arrays. Like, it doesn't take a brain science or a rocket scientist to think about how this would be complicated for IDA to deal with. And so I might come in here personally and just change this to just be an array of 400 and then just know in my head that it's 2 dimensions, just so that the IDA decompilation is a little bit cleaner. And so just something to experiment with. Just because, like, the way that the decompilation happens, like, IDA would have to reverse these transformations, because IDA would have to go from here and here to that 2-dimensional indexing, which is not always guaranteed. And so I personally, I'd probably just leave this as a 1-dimensional array. But we can also see that down here, we have A1 and then like a little 1 index, which when you're working with a structure, this is a very, very good indicator that you don't have all the members yet. Because what it's saying is that, hey, your structure is not big enough. You actually have an array of 2 of them. And it's trying to tell you that there has to be 2 of them. There's no other possible explanation for why this could happen. And so because most people are sane and not passing in like nested structures like that, or not nested, but I guess like adjacent structures, or at least like we have no reason to believe that this would be like 2 structures stacked on top of each other, I want to expand it a little bit. And so we can see that A1 at index 1 at A, which that means the immediate 4 bytes after our buffer, because that's when it's going to be stacked on top of each other. And so I want to go in and add something there. So let's edit that. Yep, int B. And then I think I saw another one, so I'm going to grab an int C. Ooh, is it double words? Yeah. And then we can come back here and refresh this. Note that when you change your data structures, you have to go in and hit F5 for it to update. But now we can see that this is becoming a lot cleaner already. And like, I don't know what these numbers A, C, and B do, but we'll figure that out later. So right away, I've distilled an input, a function that ostensibly is just setting things up, and we've identified what seems to be the beginning of a structure. Does anyone have any questions about like the structure process there? And so just to be clear, like the you can try to make leaps and like make assumptions about what the structure is, but really what you're doing is you're just trying to find ways that the structure is used and then reason about how those usages would actually translate to what the data structure looks like. And this is almost always done just by looking at how it's accessed and written to and how it's read from. So like we discovered that like, okay, we need to add 4 to this. And then IDA cleans this up and tells us, okay, now we're getting a pointer to the game board instead. Similarly, like down here, we saw 3 accesses. And so we knew that each of these accesses is likely corresponding to something. Like that's the assumption that we're making, because who's going to write a 0 to like half of a 64-bit integer? The hint is not the compiler usually. Water. But we made some assumptions, we ran with them, and now we have a structure. So let's continue. So if we head back into main, we know that this does things before input thing is actually only taking 1 argument, or at least we think it's only taking 1 argument, because I surely didn't see an A2 or an A3 used anywhere. Oh, can't hit that button. And so we can go in and type this. Like we know that this very first input here, V9, rather than it being a byte array of 419 or 416 characters, it's probably our structure. And we can see that because, how can we see that? So IDA's playing a game with us where it's because this is a array. It's saying, okay, well, therefore V9 is a pointer to that array. So if we retype this, we'll see that fix itself. So struct, what do we call that? I already forgot what we named it. I think it's called it data, right? Yeah. So struct data, and then we'll just call it, I guess, D. Yeah, now we'll call it D. But now that we've done that, instantly we can see, okay, well, now it recognizes that there's only 1 argument. It knows that we're getting the address of it. We can also look for how this is future used. So where does D go? D is also going to this sub E9A. And so one thing, so there's like a little branch point that you could do right here where it's like, okay, you could examine like how the input is processed even more now. For me, it's like I have this structure, I'm going down this line, I'm kind of a hyperfixating kind of reverser. And so I'm going to go, okay, well, I know that this structure D is used in this function now, presumably, like why else would they pass it there? And so I'm going to come in and type this and just see what falls out. So I'll change this from an int pointer to be our structure data, and that's a pointer. And when we do that, I can instantly see that right away, we've got an extra use that's happening in here that's below the structure again, because it's trying to tell us that it's an array. And so I'm going to want to deal with that at some point. And so if we can come in and look at V2, we can sort of start to reason about it. This might be something that, and when you run into situations where you're looking at things and you're going, okay, well, I'm not really sure what's going on here, it's a good indicator that you're not 100% understanding like what the behavior of the program is. And so it's a good indicator to take a step back and reason. So in this case, I'm staring at this and going, okay, well, I'm dereferencing this value and I don't know what's going on here. We can also see that V2 is clearly being used. And we can see that it's being incremented, but it could be hard to distill conclusions from this. Like, does anyone have any ideas? Like, it's not, take it from me, like this, it's not an easy function to reverse.
It's your game.
It could be my game loop. And I mean, it certainly does look like my game loop, based on like the fact, like we're returning like, I guess the result of printf check, but really just returning 0 at the end of these. And so one thing that's nice is that we have some printouts. And whenever you have printouts, just like instantly look at what's being handed to printf calls. That is a really, really good way to figure out what things are very quickly. So for example, I have 2 variables that are being passed into this printf call. One of them is saying that I took LD steps. And so instantly V4 gets retyped to like, or renamed to like steps taken with an N. And then similarly, like A1A is being printed out as score. And so now that mystery number or mystery value of A, I can now just come in and rename to my score. And this actually reveals an interesting insight now because I can find, hey, there's a location where my score is being added to. And so just game theory, that's something I'm interested in. Similarly, we can come down here and I can see, okay, I have another similar error message like score, steps taken, score, steps taken. So nothing else really falling out of the printouts is going to be super helpful. But one other thing we see is that steps taken is being written to with an I. And so I'm interested to see, okay, like what's happening. We have a for loop. We have for I equals 1. Interesting. We have a plus plus I. And it doesn't seem to be being used anywhere else. One nice thing is you can come in and when you mouse over a variable, if you hit X, or sorry, when you select a variable and you hit X, you can see here's all of the references to this. And so if I'm like, for some reason, like staring at a long function like this and going, okay, well, it's kind of hard to cherry pick out an I in all of this. So xrefs will help you verify, okay, here's exactly what's happening. And so we can see, okay, well, we start steps taken as I minus 1, but it really looks like I isn't that useful here because if it's only being used to set the steps taken, like it's just a counter at that point. But what I'm really interested in is what this v2 variable is doing. And similarly, also what C and B are. And if we begin to look at these 3 lines right here, we can see A1C and then A1B, and then they're handed into our game board in that classic like double 2D array indexing pattern that we've seen. And so with this, we could make conclusions that C and B is probably based like trying to locate something in this array. And like presumably some of you play video games. Like what are we looking at here? Yeah, we're looking at our X and Y coordinates. And so the question then becomes, okay, well, which is Y, which is X?
That's row dominant. So first C is 1.
So this is a good assumption to make, and we're going to do it. But do note that you are at the mercy of the person who wrote the program in this point because there's nothing stopping them from saying, from instead of storing like their array as XY, is storing it as YX just to confuse you. So it's good to make those assumptions. They're also good to confirm eventually, which we could confirm this, like which is X and which is Y, like for sure, because we know that this game board is built somehow based off of concrete numbers in the program. And so we could say, okay, well, we earlier noticed V3 and then V3 minus 1, which means that this 8 is going to be first and this Y is going to be second, which cognizantly, I'm going to assume that most sane programmers are going to go X, Y. So I would assume that the 8 is the X and the 0 is the Y. And this is something that I could go in and confirm if I really wanted to, but we just kind of did by saying, okay, we saw them X, Y. And so now we can say, okay, well, we know that C is Y. And then we know that B is X. And similarly, it looks like we're incrementing our score, something we don't have to worry about. And it looks like our scoring condition is when our player is at a position where a $sign happens. But we also have some other check that happens, like v2-1 has to be true, or else we hit some different logic. And it looks like what's happening is we have a v8 is v2, and then we're taking this v8 and passing it into these 2 little arrays here. So let's take a look. So we can see that this is looking kind of interesting. And then similarly, we have another one that also looks kind of interesting. And so I want to know what's happening here. Like this is something to where I'm looking at it and within 30 seconds, it's not distilling itself as making sense. And so I'm impatient. And so when that happens, I'm generally just going to try and look at it from a different angle rather than just be confused for like 30 minutes. And so I'm just going to GDB this because I want to know exactly what happens on these 2 lines. And presumably what I'm thinking is happening, like just based off of the pattern that we're looking at here. Oops, I keep hitting the mouse macros work in not the browser. Where's that function? Right here. Because what we're doing is it looks like we're saying, okay, well, we're taking our X position and then we're modifying it somehow. We're taking our Y position, we're modifying it somehow. And if we look at V9 and V10, they're checked against some conditions and then set back to the X and the Y. So presumably for me, this is like how the player, or I guess would in theory be moving around. Now, that's a guess that I'm making, and so I want to go in and confirm it for real. And so similarly, we can once again use that base trick to go in and take a look at what's happening under the hood there. So let's see, where do I want to start? Let's go right. I want to go right where we load in that for the address of that first array. So we're going to go at this offset of F1E. So let's find that process. I think it's in here somewhere. Yep. So instead of C71, I want to be at F1E. And then I'm going to give this another name. So we'll say array of interest. Oh, wrong opponent's first start. That means I also need that. All right. So we set our breakpoint. Let's run. It looks like we are stuck on taking some input. So let's just send some input. Looks like we're stuck taking some more input. Generally, when this happens, it means that you need to EOF. So Control D. Oh, wait. Control C. There we go. And I could probably... Come on, get out of there. Why can't I Control D in here? I probably have to do it in here because the tube is there. That's right. Okay. So we need to do p.send. I'm an idiot. Let's just send in some A's. 1A, singular. All right, there we go. Now we hit our breakpoint. And once again, we're dealing with like a stripped binary. So it's like we're not going to see like the pretty symbols show up, but we have IDA right behind us. And with the power of multiple monitors that I don't have, we could very quickly like reference these together or just like do some complex mosaic of the windows. But so basically we're here, we're noting that this LEA RSI is loading the address of this DWORD 15CO in. And so I'm going to grab that address. Note that I can also step once and just grab the actual value from RSI, but Gef just throws it right here for us. And I want to know, okay, what is there? And to me, I see some 4-byte ints, it looks like, because that's just kind of what I'm seeing. So I have 4 bytes of zeros, I have a 1, and then some 4 bytes. Maybe I could make other claims about this, but we know that in IDA, like we know that the type of this is DWORD. So it's going to be 4 bytes wide. At least that's what IDA thinks. That's what I'm seeing in GDB. It seems like a pretty reasonable assumption at this point to make. And so we also can see that if we look at the types, let's see, these are unsigned. So I'm pretty sure that what's going to happen is we're going to see that one of these is going to potentially be negative because like the player has to move negative at some point to go like backwards in X or up in Y in theory. And so the FFFs, like they make some amount of intuitive sense. So let's see, where do I want to go next from here? So really the last piece of the puzzle is just kind of figuring out like what's happening here, like what is V2, how is this being handled? And if this is kind of like where the last function, the last kind of arm of this bandit that we've been slowly tearing apart here, and we can see that we have to finally deal with the process input function, which is also a fun nightmare. But if we remember, like we know that this pointer to an input is a buffer. We know that V6 here is our input length. And if we look at V11, let's see what V11 is. So it looks like we're not sure what V11 is yet, but we're going to have to examine that a little bit further. So, oops, here. So we knew that this was the pointer to our buffer. Oh, I got to rename that, retype it. And then we knew that this was our input length. And so things start to make a little bit more sense immediately once we do that. We can see, okay, we have an if input length check. Great. We are setting v4 equal to a buffer. And right away, like things really start to get messy. And so this suggests to me that there's some type of data type that we're missing in here that should make things clean up. Like no one writes code like this. And to be clear, like it always does end up looking like this, but we can fix it. We can build it. We can make it better. And so right away, I can see that V12 is being split in this weird way somehow. And so that's something that I want to look at. I can also see, so like right away, like here's one thing that I'm noticing, which is that I have this V4 is a buff, like V4 is a pointer to my input. And I guess I should rename that. We'll say like buff 2, I guess. And we can see that it looks like we're pulling something out of it by taking 1 byte. So that's like that unsigned uint8, which suggests, by the way, that something is mistyped somewhere. So this is being said, so maybe instead of a character, maybe this is going to be an int8. Let's go to, it's not really know how to do that.
Int percent instead.
Thank you. There we go. Then I'll refresh that. All right, didn't make the cast go away, but oh well. Oh, the cast is for that. So we have this buff 2. We're pulling off 1 byte, and then we shift it by 4. So if I pull off a 1 byte value, and I shift it by 4 over, what happens? What am I getting? Think simpler. No math. Just what is half of a byte? Like if we shift a byte over by 4, we're effectively cutting half of it off because it gets shifted out of the register. And then in the bottom 4 bytes, or the bottom 4 bits, we're going to have essentially the upper nibble of that initial byte, right? And so maybe instead of this being a character array of 4, maybe, or 8, so like I could experiment with splitting this. IDA is a little bit iffy when you try to like split stack variables in half. So this could work or it could not work. I've seen it happen both ways, sadly. So we'll try a, yeah, sometimes it'll insert another one, but not this time. I wonder what the difference is for that. I need to hunt that down sometime. All right, but basically we're extracting 1 nibble. And then in the second one, we have V7 and OXF. And what is F in binary? It is 4 ones. So basically, we have 2 lines that are extracting nibbles. Like we take 1 byte of our input, and then V12.0 is going to be the higher nibble, and V12.1 is going to be the lower nibble. And so maybe I'll come in and rewrite this as nibbles. And this really suggests to me that this is like disastrously mistyped by IDA. But I'm afraid of trying to fix it, but going down a rabbit hole in the interest of time. So we extract our 2 nibbles, and then we enter this while 1 loop where we have a calloc here. Presumably this is allocating something that's important. We can see that our size is hex 10, so that's something to keep in mind. And then we see nibbles, V9. Okay, V9 is getting initialized to 0. And then V10 is being put there. Similarly, then we're saying V10 and 7. Now, what's 7 in binary? So just those 3 ones, right? And so what are we doing here? We're extracting bits, right? And so this function is tearing our input apart somehow. And I'm someone where it's like I can look at this, you can reason about it. I want to write myself notes so that I can reason about it. And so I can say, okay, like input splits byte into high nibble and low nibble. And then I usually give myself like examples to work with. So like FF would be split into OX1111, OX1111. And then we can see that our next process is going to be taking V10, which V9 is initialized to 0. And so we're extracting at 0, which we discovered was the higher nibble. Then let's head back here. So we'll say star result in this case. Sorry, V10. V10 is equal to higher nibble, then extract bits into result. And the way that you take notes is going to be different for everyone. My notes probably won't make sense to other people. It's just like, it's how you build up that process. And just like the more you reverse engineer, the more you take notes, it's like you build up like almost like this little language of your own. And that's something that will help you. Next, we can see that result at 1 is equal to V10 and F. All right, what are we doing here? So really, we're not doing much here. Like V10 and F, we already knew it was the higher nibble. So ending it by F doesn't do anything. Like V10 and F, like compiler magicism. But then we shift it by 3. Then what happens? Yep, we're just getting, so when we shift it by 3, we're left with that highest bit right there. So like we can say like if we had like one, that's not how binary works. If I had 0, 1, 0, 1, and then we shifted left by 3 or shifted right by 3, we're going to have a result of 0x0 because these 3 bits, 101, kind of just got dropped off into the void. And then because by ending with F, we ensured that the rest of our register was empty when that happened. And so what we've done is I have extracted 3 bits, and then I've extracted the highest bit. So our input has been split up again. We went from taking 1 byte into 2 nibbles, and then we went 1 nibble into a 3-bit section and a 1-bit section, which happened to be mapped out like that. Any questions about that so far? And so we can keep diving deeper. So the question becomes, okay, where are these stored? Okay, so we have this star result, which presumably, like, whenever I see calc in a function like this, my mind is immediately going structure, structure, structure. Or some like heap, like complex type that you want to allocate on the heap because the size could be variable. Like, let's say, and so we have this result. We can see that we're writing presumably something, which I don't know what the size of this is yet, but I can go over and check in the disassembly if my panels would change. There we go. So boom, 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 move EDX, move pan7. It looks like we're actually getting a full 8-byte value there, unless I'm totally crazy. I don't see a byte pointer there. That would be something that I probably would confirm in GDB if I wasn't trying to rush through this in the interest of time. Similarly, we can see that V8 down here is being set equal to a result. And we also have this V8 plus 1 equals result, which if we're in a loop, this means that V8 at this point is probably going to be referencing the previous result. And so now I know that because this is a keyword pointer, V8 plus 1, we know that this is 16. This is telling me that we probably have a structure with probably 2 integers up at the top somehow. And then that second set of 8 bytes is that pointer result that's being set right here. And so what I'm building is I have a loop that is appending pointers to structures. We're building a linked list. And if it's not obvious yet, we can add a local type and it will be obvious. So I'll show you because it'll fall out. So basically we have this loop. And then I'm seeing that result is being allocated, and it's being allocated with 16 bytes. Because we're saying calc 16 bytes, we're going to get 16 bytes back. A pointer to 16 bytes of data for us to use. And then we have one setting that's going, okay, at result. We have another one that's using result. And then what we can also see is that V8 down here is getting set equal to result. And then if we kind of like go forward one more step in the loop in our head, V8 doesn't actually get set again until the bottom of the loop again. So the next iteration, this V8 plus 1 equals result suggests that we're storing a pointer there. And if I have V8 equals like pre-result, and then I say V8 plus 1 equals the new result, this suggests that really what this is probably some kind of next pointer. Because in the next iteration of the loop, V8 is going to be set equal to this result, and then we'll append another next onto that one. And so every time we iterate through this loop, we're setting that next pointer from the previous iteration. And presumably this V6 variable is guarding against that somehow. Yeah, else V6 is result. And so now we can go in and add a structure that kind of like loosely suggests this. So we can say struct, let's say like input data or something. We knew that it was writing 2 numbers into those top 8 bytes, or so I'm just going to make the assumption that they're ints. That probably is something that you would have to clean up later. But then we can go, we're hypothesizing that this is a structure pointer to input data again. So let's say, like, I don't know, next. I hope that's how you define that. IDA did not like that. Need my console back so I can see this error. Okay, well, for now, let's just call it a void pointer. Struct idata in A, in B, void pointer next. Where's that going? Oh, that's probably, yeah, that would be it. We'll get it down for sure. It'd be void pointer next. Let's use our clipboard. Okay. Technical difficulties. Where's my console? Windows. All right, we'll reset it. There we go. Syntax error near int. All right, that doesn't make sense. If anyone sees what I'm doing wrong, scream. All right, let's try a char pointer. That worked. Oh wait, now they're both there. All right, I love technology. And there's the original one too. All right, technology is amazing. I say sarcastically. So now let's find where that's being typed. And so we are going to use our Y key to set the type on that. And we're going to use our struct input data pointer. And now we can see that next pointer start to make a little bit more sense. And similarly, we can also see that we've made a little bit of a miscalculation here. We assumed, 2 numbers means they have to be 4 bytes apart. But what we're seeing right here is that this very first byte is going to what looks to be results at 0, like the very, very first byte, because we're seeing low byte, and then byte 1. So this suggests we have 2 1-byte values right next to each other at the start of that, and then like 6 bytes of I don't know yet. And this is the kind of thing where you can also just play around with it until the decompilation like starts to make a little bit more sense. So let's see, uint8t, I think. It's always fun. Yeah, and then so then we get some padding in there. Note that it's always wise to add the padding yourself just so that IDA doesn't try to invent it for you, because sometimes that can be weird. And we'll refresh that, and then now we have an A and a B coming out. All right, and so then we could continue to reason about what these are. We could continue to dive deep into this program. I believe, are we out of time now? All right, I have 2 minutes left. So does anyone have any questions on like the process?
How do you refresh an item?
F5.
That works on the Dojo, doesn't refresh the whole page.
It does for me.
I probably refresh my entire like browser.
You can also go to debugger, and there's some button for this.
Okay.
But
I don't think it means it's
yeah. This is the button, or something like this. There's like a button to decompile.
It's the green button.
That says ready. Nope, now it's disabling analysis. All right, well, I swear there's some button you can hit.
I'm sure it exists somewhere.
I've never tried to mouse mode IDA before. Yeah, left is an exercise to the reader. And so basically, like, I've done some reversing on this challenge. Like, you can go in and finish out this solve. It's an exercise left to the reader. I'm also happy to help. It's not a grade or anything though, so like don't feel pressure to do it. It's just like if you want more reversing practice. Other than that, you all are free to go. Remember that Rev is due this weekend, so actually do it. And yeah, if you have any final questions, happy to help. Nothing on Twitch. We're retiring the live stream. Goodbye.